Let's study the radius of gyration. In order to find out the radius of gyration, we have to consider a rigid body which is shown in this figure, and its direction of rotation is also shown. This body is having a total mass capital M. This body is suppose made up of n particles, as you can clearly see. So, as we start our analysis, the first particle is having mass m1 and it also having its position vector r1. Similarly, for second particle, mass is m2 and its position vector is r2. Continue this analysis for n particles, mn and rn. Now, here one thing which you should consider, that the mass of all the particles is remaining constant, and therefore m1 is equals to m2 is equals to mn, and generally I am writing as small m. So the total mass of the system will be m plus so and so m, and that is n times of m. So the total mass of the system has been obtained. Now, in order to find out the moment of inertia, so see in the figure it is shown, we can find out the moment of inertia about the rotation of the axis. I is equals to m r1 square plus m r2 square plus so and so m rn square, that is equals to m times r1 square plus r2 square plus so and so rn square. Here I am multiplying the numerator as n and divide this by n. So my equation will be mn r1 square plus r2 square plus so and so rn square divided by n. Now you see this equation number 1. Capital M is equals to small n into small m. So I am substitute the value of equation 1 in my analysis. So m into r1 square plus r2 square plus so and so rn square, this whole term is divided by small n, and this is the new equation for moment of inertia, and the terms except the capital M I am consider as one constant, that is k square. Therefore, I is equals to m k square. This is equation number 2, where k square is equals to r1 square plus r2 square plus so and so rn square divided by n. Now you see, this is actually the average of position vector for n particles, and therefore I can write this as the average of position vector square, and the value of only k, if I have to find out, then I have to take the under root on the other side. So k is equals to under root of r1 square plus r2 square plus so and so rn square divided by small n. Thus, the k square shows the mean value of the square of the position vector. and the position vector is defined as the perpendicular distance of the particles from the axis, and the value of only k, not k square, is called the radius of gyration of the body. About the given axis, because in the moment of inertia the selection of axis is important, and which you can clearly observe the square root of average of the position vector, and the SI unit of radius of gyration is very easy, that is in meter, and its dimensional formula is L1. So both you can remember, and it can be asked in 1 mark MCQ, or this analysis of determining the value of radius of gyration can be asked in 2 marks, and in 2 marks you have to explain this whole theory including the figure. Now we will switch on to the important theorem regarding moment of inertia. Let's start the new topic. Two theorems regarding the moment of inertia. The first theorem what we will study in the case of moment of inertia is related with the parallel axis. So we will see one arrangement of parallel axis for moment of inertia. So here is the arrangement for parallel axis of moment of inertia. The statement of this theorem is given like this. The moment of inertia, that means I, of the body about any axis is equal to the sum of moment of inertia about a parallel axis passing through its center of mass. And the product of its mass with the square of the perpendicular distance between the two axes. So actually the moment of inertia, you just see this figure, the total moment of inertia of the body is capital I, and what this statement suggests us, that this total moment of inertia is actually the summation of the parallel axis moment inertia, that means here IC, and the product of center of mass, which we always considered as capital M, into the square of the distance between these axes, and the distance is given by M. Here we have used the subscript C because we have taken the parallel axis along the point C, and that's why the subscript C is used. So now you all are aware with the notation arriving in this figure. And now according to this law, I can write down one mathematical statement as the total moment of inertia, that means I is equals to the moment of inertia along the parallel axis plus the product of center of mass, that means capital M, and the square of the perpendicular distance between them. Here the perpendicular distance is D and its square is D square. So this is the mathematical expression for theorem of parallel axis. In the same way, we will discuss the theorem for perpendicular axis. So let's start the theorem for perpendicular axis. The main limitation of this theorem is that you can only apply this theorem to the planar body. And so here in the figure we have also considered a planar body. Here if we take x and y axis in the plane of a planar body, you see we have considered this x and y axis, then the moment of inertia of the body about z axis, means Iz, is actually perpendicular to the plane of the body, and that is equals to the sum of moments of the moment of inertia in x direction as well as the moment of inertia in y direction. And so I can write down this mathematical expression as Iz is equals to Ix plus Iy, and this is the mathematical expression for moment of inertia for perpendicular axis, because here we have considered the planar body in xy plane, so z axis is perpendicular to both, and that's why this theorem is known as theorem of perpendicular axis. In another way, you consider the planar body in zy plane or yz plane. Here you have considered for xy plane. Now suppose you choose your planar body in the plane yz, and at that time the moment of inertia of x plane is equals to Iy plus Iz. So this is for yz plane, and here x is perpendicular to yz plane. Now the remaining one is Iy is equals to Ix plus Iz, and that is for xz plane. If you consider that we have compared the equation, and in which we have conclude one thing, that mass is nothing but the moment of inertia in linear motion. Also, the moment of inertia is actually the inertia in the rotational motion. Now we will see the calculation of moment of inertia and the radius of gyration, and then we will solve some examples related to that theory.